If you want to just exit there, you can keep the papers as souvenirs. Let's see if we can't see or feel now some of the speed of these things. I'm going to go over to the course's websites here, and I'm going to go to today's lectures page where we have a couple of demo programs linked. If I go in here to sorting algorithms. So this happens to be a web page that a fellow at another university made that implements in a language called Java, or what's called an applet. But in short, this is just a visualization. It's a web-based tool with which we can now see this and some other algorithms. So I'm going to scroll down here to the bottom and choose my sorting algorithm. You can already see that the world has a bunch, and this is barely scratching the surface. We looked at bubble sort, we looked at selection sort, but there's things like heap sort and shell sort and quick sort and a whole bunch of other things. So let's choose bubble sort. What kind of array do I want? Let's choose random initially. View is just an aesthetic thing. The delay we'll leave there for just a moment. Let me go ahead and click Start and see what happens. So in this particular visualization, each of these blue bars represents a number. The shorter the bar, the smaller the number. The taller the bar, the bigger the number. So the idea is to move all the short bars to the left and all the big bars to the right. What you see as this thing runs is that it's comparing in red two humans at a time, two bars at a time. And if they are big, small, it makes them small, big. In other words, it swaps them. So notice how every time something's out of order, it swaps them. So what's really happening here? In theory, the biggest bar is making its way from left to right. But that's still not going to fix the problem. And you can really appreciate that even though we're fixing some problems here, and slowly the small bars are trickling down to the left and the bigger bar is bubbling its way up to the right, we now have to do that whole thing again. Now this speed is way too slow to be fun, so let's stop this and let's actually do this much quicker with a much shorter delay. And actually even that's a little tedious, so let's do it even faster. Let's do 15, start. So same thing. So that's one pass of Casey on the stage. That's a second pass. Third pass. Fourth. Fifth. But again, even though I'm counting these slowly, each of these passes, how many steps is there during each of these passes? Well, it's n, right? There's going to be a total of n passes. But to do a pass, Casey has to walk n steps across the stage. The reds have to go n steps across the screen. So bubble sort is indeed something like n times n, or big O of n squared, which per the chart before, is actually kind of bad. And you can feel it, right? I'm just kind of stalling here verbally. I have nothing interesting to say at the moment. But we just kind of need to kill time until this algorithm finishes, much like it will in just a moment. Perfect. So, no. So that's bubble sort. What about selection sort? What's neat about these visualizations is that what might seem like fairly abstract ideas or just common sense ideas, you can really start to appreciate what's going on if we paint a picture for them. So this is selection sort this time. Let me start it somewhat slow, but then we'll speed it up. So selection sort kind of doesn't seem like he's doing as much work at first, because notice the red bar is just kind of looking around trying to find the then smallest element. But what happens with selection sort is that he plucks out that smallest person or bar and then forces it over to the left, and then repeats, and then repeats. And so again and again, what you're seeing in red is the smallest bar that the algorithm can find on that pass. And then again, he's booting Sam or whoever's in his way, moving that bar into place, and then repeating. So on each pass, how many steps does it take in selection sort to find the smallest element? Well, it's actually going to take as many as n steps, right? You might find 2 or 3 pretty quickly, but you don't know, the computer, that 2 and 3 are the smallest until you've compared them against every other element again and again and again. So you've got n passes. Each time you're plucking off one element, so this is n times n to move n elements in place. And my God, this is really too slow. So let's change this to super fast. Now, this does not mean selection sort is faster just because I run it faster. This, again, is consistent, though, with this idea of, your algorithm is not faster than mine if you just wait a year and run it on new hardware. We really care about the fundamental differences here. So let's go ahead and do this. Selection sort, now it's really whirring along. But again, fundamentally, it's the same thing. Bubble sort is big O of n squared, and selection sort is big O of n squared. But what about this other thing? So big O is, again, worst case. What was the notation for best case? Yeah, so omega. So if we go back to this notation with big O and omega, we've got big O of n squared now. It's pretty bad. So this is big O of n squared. That's all I've been saying. What about, let's say, selection sort? In the best case, where you are handed a bunch of humans that are already in order, how much work would Casey do if she were implementing selection sort? Best case. So who thinks n squared, which was the original answer for worst case? Who thinks n? Excellent. You're almost all wrong. So why is that? Right? So selection sort is actually big O of n squared, but it's also in omega of n squared. Why? Well, Casey started over here. And again, suppose the humans are 1, 2, 3, 4, 5, 6, 7, 8, all in the right order. What was Casey's first suggestion to us? Well, find the smallest element. How did she do that? Well, she looked to her left and said, oh, here's number 1. But did she know at that moment in time that 1 is the smallest? No, she only knew that once she checked here, and then here, and then here, and then here, increasingly disappointed that she's not finding anything smaller. But only once she got to number 8 could she definitively conclude that was, in fact, the smallest number. So what does she do? She makes no swaps. She knows 1 is in the right place. Next, what should she have done? Or would she have done? Find the next smallest element. So she can now ignore number 1, but she now needs to start at number 2 and says, OK, 2 is now the current smallest. Let's see if there's anyone smaller. 1.5, something like that. Well, let's see. Nope, 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 nope. Nope. So only once she does another n minus 1 steps does Casey know definitively that 2, in fact, was the smallest. What's she going to do again? Same mistake, same mistake, same mistake. So as elegant and as simple and as sort of commonsensical as selection sort is, it's always n squared. Because you don't have this sort of omniscient view of your data. You only check for the current smallest element. And to do that, you have to check everyone else. So that's n squared. What about bubble sort, though? If I instead revert to bubble sort, which was the second algorithm, where Casey just swapped pairs of people, but then did it again and again and again, we said that in the worst case, that's n squared, if people are reversed ordered. What about in the best case? What if all those volunteers came up and they were 1 through 8 in perfect order? How much work would Casey do with bubble sort? So it would be n, right? And if you're just kind of playing the odds here, most likely the answer to this question is going to be the opposite to the other one. So indeed, the answer here is going to be n. But how? So bubble sort does have a potential optimization. In the worst case, bubble sort n squared, no doubt about it, because in the worst case, everyone's out of order, and we kind of walk through just how much work you have to do to re-bubble everyone through. But in the best case, what might Casey be able to do to optimize so that she stops wasting her time if everyone's already sorted? She first compares 1 and 2, not out of order. 2 and 3, 3 and 4, 4 and 5, 5 and 6, 7 and 8, done. So what could Casey do? She could now go back to the start and do it again, but what could she do instead? She just needs to leverage some piece of information she just created for herself. No swaps. So what if Casey, in her implementation, just has a variable initialized to 0, and that's just a counter. And anytime she does a swap, she does plus, 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 plus. If she does any swaps, that means, you know what, we've seen this before. Just because I've done swaps doesn't mean the problem is solved. I better go do it again. That should be her reasoning. But if instead she makes a pass through these humans, makes no swaps whatsoever, what should she obviously do? Right? It would be downright stupid to do it again, because if you didn't change the state of your world, if you didn't change your array and the answer you got was no swaps, what are you going to get if it's an answer the next time? Well, no swaps, no swaps, no swaps. So what's the opportunity here? If counter equals 0, exit. And so bubble sort, by contrast, is absolutely big O of n squared in the worst case. But in the best case, we would say it's instead omega of n. She still has to check everyone. It's not omega of 1. It's not constant time. She can't just glance at number 1 and say, feels like it's in order. Still has to look at all n, but that's why we get omega of n. So this isn't bad. This is feeling kind of good, and especially when we speed up our CPU time, it's looking really good. But remember where we started. This was counting people 1 at a time. This was counting people 2 at a time. This was having you guys count yourselves sitting down half at a time again and again and again. But again, n squared is not the best place to be in. This here, down at the bottom right, if we zoom in, that's what n looks like. It's still a straight line. We've just kind of futzed with the x and y axes to stretch things out. But n is still straight as a line there. But if we scroll up, n log n, that's interesting. We'll see that guy before long. But n squared, who we've seen today, that feels bad, right? That means that if your size of your input is, say, my God, this is only lining up at like 4 or 6, whatever the unit of measure is here, that's bad. It's going to keep growing faster and faster. So with something like bubble sort, sorting these elements is going to feel slow unless you do something better. But thankfully, there are smarter ways. And again, per this promise of teaching us how to do things more efficiently and effectively, let's just get a sense of how much better we can do. So the world has come up with, again, yet more sorting algorithms: stooge sort, q sort, j sort. I'm going to choose our familiar one. So I'm going to choose selection sort in this box. I'm going to choose bubble sort in this one. And then I'm going to choose another guy, merge sort. We haven't looked at merge sort, but someone put a little more thought into implementing that algorithm. It's still just as correct. All 3 of these are right. And Casey, in our demonstrations, no one did anything wrong today, but we can do better. So what I'm going to do here, and these examples are very similar. It's just this, the person who implemented this rotated the bars so that they're now sideways instead of top to bottom. But it's the same idea. We want to get short bars on one end of the graph and long bars on the other. I'm going to click as fast as I can on all 3 of these graphs to have them run simultaneously in hopes of demonstrating which one is better. So let's just see, after a little bit of thought and a little bit of CS50, how much better we can do. Here we go. Done. So that is merge sort. This is CS50, and we will see you next week.